Hey guys, it's Terry, and I thought I'd take the opportunity right now to record a whiteboard session that answers a question posed by one of my students in the CCIE Routing and Switching written online course that I've been teaching. And that question was, what is a QnQ tunnel? Well, to attempt to explain it, what I want to do is I'm going to illustrate a scenario where we have a series of switches, SW1, SW2, and SW3. Now, these switches belong to us for the purposes of this discussion, and they are interconnected. For instance, SW1 and SW2 are connected by ports 18 through 20, and SW2 and SW3 are connected by ports 23 and 24. Now, what we're going to be emulating here is going to be a service provider network where we are going to be the service provider. So the service provider elements are going to be SW1, SW2, and SW3. Now, just to further work with some of the technologies that we've been discussing in the course, I've configured these three ports, or these three links, to operate as an ether channel, and that's going to be PO12. And these two are going to be operating as port channel 23. Now, the reason I did that is I wanted to get rid of some of the components associated with the spanning tree so that we're just focusing on a straight through network. Now, these port channels are working as .1Q trunks. Now, we can see that by bringing up the gear itself and just take a look at the output that we get when we do the show interface trunk command. For instance, on R1 we can see clearly that PO12 is a 802.1Q trunk. We can go over to SW2 and we can look at the output of the same command, show interface trunk, and we can clearly see that we have those port channels that I discussed, 12 and 23, and they're operating and trunking. And just as the last final check, we'll do the same thing on SW1, show interface trunk, and we can see that port 23, or port channel 23, is operating as a 802.1Q trunk. Now, the fundamental idea behind this is going to be the fact that we are going to end up moving traffic in such a fashion that we have two .1Q headers, or tags. Now, what we'll do to illustrate the idea or the concept will be we'll connect R1 to SW1. Now that means Fast Ethernet 00 is connected to Fast Ethernet 01 on SW1. And we'll use BB3 in our topology to act as the other end. So that means we're going to be connected at FAO 13 on SW3 to FAO 1 on BB3. Now, we'll create a series of VLANs. We're going to create two VLANs. We'll create VLAN 13 and VLAN 31. We'll use the IP address range of 13.13.13.0/24 for VLAN 13, and we'll use 31.31.31.0/24 for VLAN 31. Now, the numbering sequence we'll use is we'll use .1 for R1 and .3 for R3 or BB3. And in order to make this work the way we want to, we are going to create sub-interfaces. For instance, we'll create 0/0.13 and 0/0.31. And we'll do that on both of these devices. So it'll only in this instance it will be 0/1.13 and 0/1.31 on BB3. Now the concept here is we're also going to create a VLAN. That VLAN is going to be VLAN 100. And that VLAN will be propagated or populated on all three of the devices inside of what we're referring to as our service provider cloud. Now, what's going to end up happening here is we are going to be first queuing the frames or tagging the frames as they're created on R1 and BB3. But in order to transfer them through our switching infrastructure, we are going to tunnel them through VLAN 100, and we are going to be assigning the second tag. Now, this second tag is oftentimes referred to as a metro tag. That's why this technology is predominantly mentioned or discussed in the form of Metro Ethernet. Now, we'll discuss another technology called MPLS that uses some very similar terms as far as provider edge devices and things along those lines, and provides service across a fabric, in this instance a routing fabric, that does some similar things. But the benefit, the fundamental benefit of Metro E, or this metro tagging, or this QnQ concept, is the fact that we do not have to run a routing protocol or a static routing process between our customer equipment and our provider edge equipment, where SW1 in this scenario would be a provider edge device, so it's at the edge of the service provider environment, and of course BB3 and BB1 would be representative of the concepts of customer edge devices. Now, the element here is that we want R1 and BB3 to be able to interact using layer 2 technologies. For in this instance, we're going to want them to be able to trunk to each other. Now, that's not a problem in of itself, because we've done things like router on a stick and things like that in our previous discussions. But what we want to make certain is that we do not want these customer devices to participate in our layer 2 infrastructure, nor do we want to participate in their layer 2 infrastructure. So the ideal tool for this is going to be referred to as a .1Q tunnel. Now, for the purposes of our discussion, we're also going to mention another tunneling technology that we're going to talk about, or that we'll mention later on, which is going to be our layer 2 protocol tunnels. Now, a layer 2 protocol tunnel can work with CDP, it can work with spanning tree protocol, it can work with VTP, and it can even work with our port channels, or what we refer to as our ether channel configurations. So let's take a quick look at this and make our configurations on our respective devices. So what we'll do is we will bring up R1 first. Now, in order to make this operate, we need to make our configurations on R1 such that we have our virtual subinterfaces. So in order to do that, we'll go to interface FAO1 or FAO, and we'll specify it. We'll just use 13 so that we can make reference to that being in VLAN 13. However, in order to actually make it work as part of VLAN 13, we need to use encapsulation, specify the type of encapsulation, and here we'll make reference to the actual VLAN ID that's going to be used in 802.1q. So here it will be 13. Once this is done, we can apply an IP address. We said we'd use 13.13.1. We'll give it a /24. And once that's done, all we got to do is go in and create the 31 subinterface, encapsulation .1q 31, and we can assign it an IP address now. 31, 31, 31, 1, and we'll use the /24. Interface FAO will go up to the main interface, and we will no shut it. Now once this is done, show IP interface brief. We'll take a look at these interfaces, and I'm just going to exclude any unassigned addresses. We see now that we are running these two subinterfaces with the following IP addresses. However, we note that our line protocol, the line status is up, but the protocol is down. So let's go over to SW1, and I think we'll find out that SW1 is turned off, or SW1 FAO1 is turned off. So show interface FAO, show run interface FAO1. Yes, it's shut down. So let's take care of that. Config T, interface FAO1, no shut. Now once that's done, our interfaces over here should come up and everything should be good to go. We can see that we're up now. So let's go over to SW1. Now, the issue here is that we haven't done anything special. There's no, this switch, even though we're running trunking or encapsulation for trunking on the other end at 802.1q, is not going to negotiate a truck out this interface. The reason why is that R1 is not going to work with DTP, Dynamic Trunking Protocol. So we can see the actual nature of this Fast Ethernet 01 interface by doing do show interface FAO1 switch port. Now we can see now that the switch port is enabled, which means it's not in shutdown mode. It's configured to operate administratively in dynamic auto, and since this is a 3560, that's going to be its actual default condition. But by virtue of the fact that we've received no DTP coming from R2, we are not, R1, we are not going to negotiate a trunk. So we're going to sit here in static access. Now, previously, when we did router on a stick, we would go in and we would actually configure this as a trunk. We would go switch port trunk, would specify the encapsulation .1q. Once that was done, we'd come up and say switch port mode trunk. But we don't want to trunk, because if we did, that means SW1, SW2, and SW3 would have to know about the VLANs that are being employed by the client, specifically VLAN 13 and VLAN 31. Now, we said we were going to use VLAN 100 to accomplish this task, this QnQ tunneling configuration. But let's take a look at some of our other modes. We know we can do switch port trunk or switch port mode, and we can specify access, or we can specify trunk. But let's look at some of the other features. We'll use the context sensitive help, and we'll notice immediately we have this notion of the .1q tunnel. So let's make that configuration here. Now, here is the scenario. What VLAN is automatically assigned to FAO1? We'll repeat the do show interface FAO1 switch port command, and we'll see that it's VLAN 1, and that's not what we want to work. That's not how we're going to have this configuration, because if we leave it the way it is, what's going to happen is that when we try to create this tunnel between SW1 and SW3, we're going to use VLAN 1, and we don't want to do that. Because VLAN 1 is going to be the default for any operational interfaces that we have that are going to be in switch port mode. We said that we want to do this in VLAN 100, so we'll go ahead and make that specification. Switch port, access, VLAN, and we'll specify 100. Now when we come up here, we'll see that it's now operating in 100, and note now our operational mode is tunnel, where our administrative mode is tunnel. But we're not running DTP. So one way to turn off DTP on an interface would be to configure the no negotiate command, could be to configure it to access, but also enabling the tunnel mode is going to turn off DTP. And we can see that clearly here. We didn't tell the router to turn it off. So the key element that we want to look at now is the fact that VLAN 100 didn't exist. So we can see here it created the VLAN, but we're not running any spanning tree. So the question is how do we know that? We'll type do show, sorry, we're not running VTP, do show VTP status, and we'll note immediately that there is no VTP domain configured. So that tells us automatically that we're not running VTP. So what we'll need to do is let's go to SW2 just so that we don't forget it, and we'll create VLAN 100 across the board on SW2 and SW3. Switch or VLAN 100 exit, so we don't forget. Now we know whatever we've done, do show run interface FAO1, we need to make mirroring configurations on SW3 on port FO13. So let's do that now. Interface FAO13. Well, first, actually, we didn't configure anything on BB3 with regard to our FAO1 interface. So let's do that now while we're thinking about it. Config T, interface FAO1 13, encapsulation .1q, and we'll use 13. IP address 13, 13, 13, 3, 255, 255, 2550 for the /24. And let's do the same for 31. IP address 31, 31, 31, 3, 255, 255, 2550. Interface Fast Ethernet FAOO, no shut it. And we should see show IP interface brief, exclude unassigned. We should be up and up, which we are. Let's make sure we stay that way, which we should. So that tells us that our interface do show run interface FAO13 is actually configured. So it's not shut down. But we don't want to operate in this mode. We want again to use that tunneling configuration. So let's go there. Interface FAO13, switch port, access VLAN 100. Then we're going to do switch port mode .1Q tunnel. Now, the interesting thing here is that we're seeing a notification. It's talking about the MTU of 1500, and we'll discuss that later when we go through here. But what ends up happening is by virtue of the fact that if we send a packet size of 1500, what's going to happen is by virtue of the fact that we're adding the second .1Q tag, we're increasing the overall size of the frame, which means we have to make certain that our switches accommodate that by going in and adjusting the system MTU. And that's going to be done by saying system MTU, and then we specify the size, like 1504. Now let's take a look and see what it is right now currently. Do show system MTU. It's currently 1500. So if we were to change it to 1504, we'd have the capability of being able to send pack or frames up to 1500 in size and still deal with the actual second .1Q tag. Now that this is configured, we should have reachability between our devices. So let's do a ping. Let's ping 13, 13, 13, 3 from R1. We should lose one ping from our ARP request to identify our neighbor, and then we should be able to have 5 or 4 consecutive echo replies come in, and we see that. And obviously we can repeat the process and we should have no loss, because we should now see something in our table. For instance, show ARP 13, 13, 13, 3. We see we have the MAC address here, so we don't have to repeat the ARP process. And this, of course, will age out over time, but it is in there now. So let's do this 31.31.31.3, not ARP, but ping. We'll lose one to ARP, and then the other 4 should succeed. So keep in mind, we have reachability between R1 and BB3 because of this tunnel that we have built across our infrastructure. So to make it clear, we have created a tunnel between SW1 and SW2 that actually employs VLAN 100 for the purpose of providing this transport without any of our devices, SAO1, SAO2, or SAO3, knowing anything about VLAN 13 or 31. And we can again illustrate this point. We'll go to the middle here and do show VLAN brief. Notice that there's no mention of VLAN 13 or 31 anywhere between VLAN 1 and VLAN 100, which we're using for the purposes of transmitting our information. Now if we go over to SW1, do show VLAN brief, we'll see that VLAN 100 is indeed physically assigned to Fast Ethernet 01. So that should clear up the entire idea behind this and the fact that we're double tagging. So what happens is we have a .1Q tagged frame that is being tagged as the payload inside of another .1Q set of frames. so that we can transport them across our infrastructure, us being the service provider, without us having to be concerned with what VLANs the clients are running, and that protects both us from the clients and the clients from us as the service provider. Now, what I would like to do is illustrate one final point, and that's we'll go through and we will do the specification where we can successfully ping, but what happens again? Let's mention that whole point of what if we specify the size of 1500? The information's leaving R1 at 1500, which means it cannot be tagged again because the switches aren't going to deal with it since it's going to be above 1500 bytes in size. So let's try that. We will not be able to successfully ping the address. 4 fails, 5 fails, and it's done. So let's go over to SW1 and make those changes. Now this is going to require a reload of our switches. So system MTU 1500, exit right, and we'll go ahead and reload. Actually, no, not yet. Config T 1504. Do right. Notice it tells us these changes to the MTU will not take place until after the reload is done. So let's do the reload. Do reload. Let's go over to SW2. Config T. System MTU 1504. Do right. Do reload. System MTU 1504. Do right. Do reload. So we'll wait for the switches to come back up. I'd paused the video, but I've been having trouble picking the video up after I've paused it, so we're just going to let it run. And in the interim, what we'll do is let's talk about some other elements here. For instance, show run interface FAO. FAO. We haven't done anything special on there. FAO 13. I'm basically just waiting for the devices to come back up. So 13.3 encapsulation. So there's no new configurations visible to us on these devices. So let's sit here and wait for SW1 and SW2 and SW3 to come up. If I was more entertaining, I'd think of a joke to tell everybody, but I promise never to sing or tell jokes on videos. Almost there. Always seems to take SW3 so much longer to come up, but it's a 48 port switch in my topology. There we go. SW1 is up. We should not have to do much waiting here. SW2 not up yet. So while we're here, let's do show CDP neighbors. Now bear in mind SW2 and SW3 are coming up, but notice that we don't see R1 in our list. Let's give it time. Maybe it's an issue with regard to CDP. So for instance, if we take a look here and say show CDP, you're going to notice it's going to send hello packets out every 60 seconds. We got a hold timer of 180 seconds. So it may just simply be an issue of waiting. So show CDP neighbors. Okay, now SW2 is up, but we're still not showing any connection to SW or to R1. Show CDP neighbors. Let's take a look at the interface and see if it tells us why. Show run interface FAO1. Notice here, no CDP enable. The moment we made the configuration switch port mode .1Q dash tunnel, the system automatically entered that information, or entered this configuration to turn off Cisco Discovery Protocol. Now we have other tools we mentioned, which will allow us. Let's see here in show CDP neighbors. Let's see. Do we see our connection to SW2? We do. So let's go over to BB3. Show CDP neighbors. Same thing. We don't see anything connected to this device. Now, if we want to alter that behavior, what we can do is we have the ability to leverage another feature which we mentioned previously on the whiteboard, and that's going to be this notion of our layer 2 protocol tunnel. The layer 2 protocol tunnel can actually enable us to make the configuration such that R1 thinks that it's physically connected to BB3. Now, we've spent a great deal talking about logical versus physical topologies. This up here, R1 connected to SW1, connected to SW2, to SW3, to BB3, is the actual topology. However, we still have this logical connection that we've been discussing regarding using VLAN for the QnQ tunnel. Now, we noted specifically that CDP has been deactivated on both FAO1 and on FAO13 on SW1 or SW3 respectively. But what we can do is we can also use this concept of the layer 2 protocol tunnel to have R1 directly exchange CDP hellos with BB3. Now, what we'll do is we will continue to leverage VLAN 100 to accomplish this, but this is not part of the 802.1q tunneling component. All we're going to do is make a configuration such that R1 thinks it's directly connected to BB3, and we're going to accomplish that by tunneling our layer 2 protocol, specifically CDP, between the two of them. And we can do that very quickly by going to SW1. We go to the interface FAO1, and we're going to make the configuration for layer 2 protocol tunnel, and we're going to specify CDP. Now, we could also specify a number of other items to include STP, VTP, that's spanning tree protocol and VLAN trunking protocol, and CDP. But also I want to point out here that we can go ahead and configure point-to-point, which opens a number of other options that include our ether channel negotiation protocols of link aggregation control protocol and port aggregation control protocol. Keeping in mind, port aggregation control protocol is Cisco proprietary, and link aggregation control protocol is going to be the industry standard. But it doesn't end there. We also have the capability of utilizing unidirectional link detection between these devices. But only thing we're going to configure for the purposes of our discussion is going to be the CDP configuration, or the tunneling of CDP between SW3 and SW1. So here we'll go to interface FAO13, and we'll make the same configuration, layer 2 protocol CDP. Once that's done, we need to give the system time to exchange hellos. But once that's accomplished, we can go over to R1 and type show CDP neighbor, and after the hellos have been exchanged, we will see that we have formed our neighbor relationships. So let's go over to BB3, show CDP neighbor, show run, make sure I got the configuration right. Layer 2 done. Go over to config T to show run interface FAO13. Make sure I did it on the right interface, which I did. Should have had enough time now to have everything synchronized, and as we can see, BB3 thinks that it's physically connected to R1. So that should conclude our discussions about QnQ, and I went ahead and tossed in the layer 2 protocol tunneling as just a little bit of an extra, and I've got other questions coming, and I'll try to get videos out for those as time allows. So hope this was helpful. Have a great day. Bye.